Let's look at another way that we could describe a surface over which we can calculate a flux integral. So think back to triple integrals in cylindrical coordinates. Cylindrical coordinates have two lengths and one angle. So there's a r, a theta, and a z. So in constructing dv, we can't just use d theta, dr, dz because d theta is not a length. D theta is a change in angle. If we have a change in angle, we care about, to turn it into a length, we just multiply by how far we are from the origin. We just multiply by r. So now r d theta is an arc length, and now we can approximate dv as a little cube, r d theta dr dz, for a length, a width, and a height. So let's imagine integrating the flux through a cylindrical surface. The basic flux integral always looks the same, integral over a surface of a vector field dot dA. What we're going to do now is change how we describe the surface. The surface is a cylinder with a radius of r. So if we're flowing through the surface, I need to evaluate the vector field at all the points r, theta, and z. So notice that the r is the fixed radius of the cylinder because we're flowing through the cylinder. We care about flowing through the surface of this cylinder. So we don't care about what's going on inside, we care about the stuff inside the cylinder flowing out of the cylinder. But we need to describe the dA. So we need an expression for the dA. We need to write the dA in cylindrical coordinates. So let me just write down what it's going to be, and let's see if it fits. So what we need, we're going to integrate the function evaluated at r, theta, and z. And I'm going to top down this. So it's going to be dot cosine theta I plus sine theta j. Then there's an r d theta dz. So all that is the dA. So this is how we would calculate our flux integral through a cylindrical surface with a fixed radius. Let's think about what our surface is going to be. We could think about the values that we describe here are going to be, so it's going to be a double integral. So there's going to be a theta integral and a z integral. So here's what we want to do. We want to think about why this expression is going to fit for dA. Then we're going to want to think about what different values of theta and z mean for the surface. What are we talking about with these different values of theta and z? Where's that R from? What do all these pieces mean? What's this part? So where do we get that vector? Where's the R from? D theta dz, we knew we were integrating over a surface in cylindrical coordinates, so there's got to be two deltas, a change in theta and a change in z. We're on a surface with a fixed radius of r, so the radius ain't changing, so those two are going to be our variables. And what happens with different values of theta and z? This is what I want you to think about when you think about integrating the flux through a cylindrical surface. All we've changed here is how we are describing the surface. That's the key thing to note. All we're changing is how we're describing the surface. That's the change from this formulation to the previous formulation. Any questions? I was right on the verge of like just going through this forward when I decided, nah, I'm gonna write down what it is and have you think about it for a while. Any questions? Comments? Snide remarks? Here are the things that I want you to think about. Where do each of these things come from? What happens if we change values of theta and z? How does that affect? What parts of the cylinder does that get us? Where does this vector come from? The cosine theta I plus sine theta j. What about this r? Where does that r come from? D theta and dz, they're just taking the place of the x and the y. So that's what I want you to think about. Why does the dA look like this in this problem? Then ask the same questions if we're looking at the flux through a spherical surface. All right, let's pause the video here and talk about what's coming next.